with that idea, there is something called a stratification, which is what people would like to do. There is a problem with full factorial experiment. Okay, I practically want this to be animation, but that is okay. Okay. So, the deal is, if you take a 3 variable case, just look at this, this is very similar to what I just showed you just now, that inscribed circle. Okay. So, now take this x1, okay, and you can see that there are about, at this 0.5 there are 1, 2, 3, 4, 5. Okay. Similarly, at this 0 there are 5 dots, and at 1 there are 5 dots. Okay. So, if you are viewing from this side, meaning this particular plane, okay, this plane x2, x3, this particular plane, if you are looking at it, if you are viewing from this side, what information are you getting with respect to x1? No, the x1 value is fixed at 0, but you are getting 5 different values. Okay. But in terms of x1, what are you getting? You are getting only 1 point per, you are not getting the 3 information, you understand, only the shadow. When you are seeing from this side, when you are seeing in this direction, you are only taking the points that are in this plane. You do not have any other information, because this is a projection. When you take a projection of x1 and x2, sorry, x2 and x3, you are taking only 1, 2, 3, 4 times. So, 20 point information only you are having. When you take a projection, only these 20 points come, but how many experiments you have conducted? At each of this design point, you are conducting an experiment. You are conducting 60 experiments you have conducted. In total, I have conducted 60 experiments, but when I take a projection, how many information I am getting? I am getting only information corresponding to 20 points. So, there is a problem with the full factorial experiment kind of a situation. When you put them right behind each other, in a projection sense, you are getting only a fraction of the information outside. So, the uniform, the sampling, the idea on the uniform exploration is great, but then if you place them right behind each other, you are losing information. So, people wanted better ways to do it. Okay, that is what is. So, this idea was just to tell you that if you see from the top, what do you call, like a marching thing, okay, it is similar to a design of experiment. Okay. So, people are uniformly placed, right, but then if you are seeing from this angle, so this is x1 and this is x2 perpendicular to the thing. If you are seeing from this side, I am seeing only one guy, correct. That does not mean that there is one guy, there are 20 other people in that line. So, only this guy's information I will get when I see from this side, from that projection. That is all the idea is. Okay, that is why this plot was put here. Okay. So, let us say that I want to see the remaining people's face. Obviously, I cannot change the camera location, I am only seeing from this side, right. So, if I want to see the other people's face, what should I do?
Viewpoint.
Sorry?
Change the viewpoint.
That is what I told you to begin with. I cannot change the camera, that is what I said. I am seeing from here. So, kind of. Okay. I asked this guy to come out a little bit this side, the third guy to come out a little bit that side. Okay. But then the fifth guy again comes behind the third guy, that I cannot see him. Okay. So, I want to perturb these points a little bit. So, I cannot go, if I do that and then I see from this side, I do not guarantee that I will get 60 experiments information, but I might get about 55, 58 information. You get the point, right. So, if I ask these guys to just go perturb themselves a little bit, I may not be able to see all of their faces, but I might be able to see most of their faces. That is the idea about, because each experiment costs you and you want to take that much information and you do not want to have any bias also. See, that is the advantage of orthogonal array per se. What it does is, it does not give you a bias, that 1 minus 1 and all. It is not giving you a bias with respect to a particular level. It says both levels I will do the same, because I have no information about favoring one particular level. Okay. So, if you project this is a full factorial, if you project a particular variable, the points overlap in each other across, so you lose information. Instead, if you can do this kind of a thing, that is called a stratified sampling. Okay. So, one such stratified sampling is what the LHS stands for Latin Hypercube and S stands for sampling. Okay. This Latin is nothing but the Latin square that we are talking about, -1 to +1. Okay. This hypercube is, this is a square, but then n dimension it can be a cube, then fourth dimension I cannot draw, it will become a hypercube. So, generalization is Latin hypercube sample. In 2 dimension it should just be a Latin square sample, okay. But then square is just a simplification, simple case of a hypercube. Okay. So, the idea is I would still like to preserve the uniformity of the sampling, meaning from an exploration perspective, not from the sampling perspective. That uniformity I might want to keep in terms of all the dimensions. If I am using 5 samples in this particular dimension, I want to use 5 samples in the other dimension, and I want to explore each of the grid also. Okay. So, in all the dimensions you want to do the stratified, and projection onto the variable axis is uniform. Okay. I do not want to get extra information on any particular variable axis. If I am getting 55 on that axis, I should get 55 in this axis also. Okay. So, the idea is one such combination, this is an outcome of a Latin hypercube sample, we will discuss that. Okay. What this one says is, I am just going to, it is already bolded there, but I am just showing it. Okay. This is one of a Latin hypercube output. What it says is, if you see in this particular row and column, there will be only 1 1. So, if I do this, similarly if I do this, I will cover all the entire design space. This is uniformity. So, you can do the same for any other thing also. This is the one that we are talking about in terms of uniformity, not about the sample placement. If you take 2, I did not expect, but this is an interesting case. Okay. So, what is happening? This row and this column I get rid of, this row and this column I get rid of, this row, this column, this row, this column, sorry. Still I am taking care of the entire domain. Okay. So, you can do this for any variable you want, but this is only one of the 575 combinations you have for just a 2 variable case. Okay. I could have like this 1 3 4 2, okay, instead of this. So, if that is the case, then 1, this guy is gone, this guy is gone. So, I need to choose out of these, let us say that I choose, no, I am not going to spend time doing that. What I am saying is, you can also get other configurations wherein whatever I discuss now will be satisfied. How many such combinations will be there? 575 such combinations will be there. And just now as I showed you, this is also a case. But does that give me any information on the design space? It is not exploring half of the design space at all. This side is not explored, this side is not half, almost 100% of the design space is not at all explored. It is not giving me any information. So, though I preserve the projection on the independent variables to be variable axis to be uniform, I might end up not exploring the design space at all. So, I want some other criteria as well. So, we will see what, and for 8 variables I do not even know what is this called in European sense. Any idea, man? 1 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry, 3, 6, 9, 12, 15, 18, 20 zeros, 1 followed by 20 zeros, I do not know what that number is. For 8 variables, these many combinations are there, you can do this. Okay. So, the point is, you want to choose, you want to come up with some other combination, some other criteria that will give you the best exploration of your design space. Just to give you a 3D example, Okay. So, what the same idea here, let us say that this was x 1, x 2, x 3, okay. I have 10 points, I guess 2, 3, 5, yeah 10 points. So, what you do is you grid each, you remember, right, d dimensions k grid we did. So, 10 grids you make. Okay. Then what you do is this is a projection, please understand this is placed in 3D, but I am just showing you a projection. This is the uniformity that I am talking about. Some algorithm I have placed this 10 points in the space. I put 3 of you in 3 different directions. You are seeing from outside the room, he is seeing from this side of the room, and I am seeing from the other side. Okay. So, we can only see projections, we cannot see where it is in the space, you can only see projection, that is what your naked eye can see. So, this is for that person's perspective, this is for my perspective, and this is for that guy's perspective. But if you take any of the projections, they will all be the same. I do not want to spend time doing 10 by 10, but that is what it will do. Okay. When you put a point, you will lock that particular column and row, and then you go look for other columns and rows where you want to put the points. So, because that is taken care of, that is what it is. Okay. So, now no, I have more points, then you create additional grids. So, you can offer 20 points, then you do 20 by 20 by 20 and then you do that. Okay. So, but you can see, but this is not a great stuff, there is so much of space left out. It has got to do with two things, maybe this is not, I need to come up with some other criteria because these two are very closely placed, these two are very closely placed. Okay. Maybe if they are placed somewhere here, these two are very closely placed, these three are very closely placed, given that I am exploring this entire space with only 10 variables. So, I need to come up with a criteria where I want to send them, not only preserve the uniformity property, but also I want to send them across my design space, because if you see like that is what, there is huge blanks all around. Okay. How do we do that? So, that is called space fillingness. Until now we were only talking about LHS in general, but the property that I am talking about right now is called space fillingness. So, what they say is this, this is something that we already spoke, right. You can also do a x 1 by x 2 and then you can take the diagonal elements, it will still satisfy. Okay. That is the first one which we have discussed. So, some measure is required to judge the LHS from a exploration perspective. Simple thing called a max-min algorithm, it is available in MATLAB. Max-min algorithm is also used in many other stuff. So, what it is saying is you maximize some minimization problem. Okay. So, what do they do is for instance error, okay. You take a 4 bar mechanism which is going to give you this kind of a curve. You know what a 4 bar mechanism is, it does not matter, let us say a robo is kind of giving you a graph, but the robot does not go and draw the graph like that. It gets inputs at many points, okay, and then it is just going to go connect those points. Okay. Now, what happens is at each of this point I could have an error. In such a case, what people will do is they will say that you want to minimize the errors at each of these points, minimize error at each point, okay. Then find the maximum of those errors, because that is the one that I want to take care of. Let us say this guy had 0 error, I should not worry about this guy at all, but this guy had maximum error. Okay. So, in general you want to minimize the error, but I want to capture the maximum of the minimized errors. Okay. So, the max-min algorithm for sampling, what does it say? Just be with me, we will take a break soon. There are multiple points here. I take one point, I find the distances d1, d2, d3, d4. Okay. It is not done that way, but I am just saying. Okay. Then what I do is I go back, give them into a DI array and then I sort them, that is what is this one. D1 to M ordered distances between all possible pairs of points. So, all possible pairs, this point, this point, this point, this point, this point, this point, okay, that is D1. Now, what I want to now let me not tell that. So, the second one is J1 J2, okay. So, I took D first, the second one that I am taking is Ji. These are the number of pairs of points separated by the same distance di after I do this, okay. In the back I also have an index that says these are all the different. For the same distance d high, I see what are all the points, how many of these guys, you know, that pairs, I number the pairs and then I look at it. So, what I want to do is I want to maximize this d. I want to put these points as far as possible, so that I explore the design space. I want to maximize D1, okay, and minimize J1. Similarly, I want to maximize D2, minimize J2. If you go to the book, there will be a theorem that will generally say maximize Di while you minimize Ji, okay. But there could be a case where you will have to keep doing this in a consequent sense, okay. That is why I wrote it like this. Maximize, you want to maximize D1 while you want to minimize J1, meaning the number of pairs that share that distance, you want to minimize that. That is why this is a max min, and you will have to do this simultaneously, because as you move this point, all the distances get affected. You understand what I am saying? That is why LHS becomes a little trickier when you try to use it for higher dimensions. When I say higher dimension, even with 10 variables, if you do LHS, what happens is you throw 1000 points. It will take overnight to do, because what happens is you will have to, it does your distance every time it goes and recomputes your distance, okay. So, okay, so what do I mean by the distance? In this particular case, in a 2D case, it is just a Euclidean distance, okay. So, this P can be a 2 in a 2-dimensional case, and or you can have anything, but as it is also pointed out in literature, people say that we will use a Manhattan distance, we will use Mahalanobis distance, you can use any distance, nothing seems to be superior to the other one in this kind of a study, okay. So, then what people said is this becomes little trickier, because you will have to keep going and doing that, and finally they came up with a slightly different criteria, okay. There is a little bit of algebra coming from this to here, which is slightly out of scope for this course. So, what we will do is we will take it for granted that you do this as a sum for all the points basically. J is the number of points, right, I mean J is this guy, J runs from 1 to M combinations, Jj each pair that I take, Dj raised to minus q, and 1 over this is the same 1 over q that you take, okay. The q is usually defined by us, we usually keep it as 0.5, but you can also change it accordingly, okay. So, this is the criteria that you want to max min, that is what you will try to do. This is the criteria that you want to maximize, I mean you use the max min algorithm to deal with this particular criteria, okay. This is your LHS phi criteria that they say. So, there is one limitation though to do this. What happens is, I told you, I give you a cluster and I told you the cluster is in your hands for 1 day, 24 hours. You give me a sampling response, you sample and you give me a response, okay. But I just told you, and then I told you that your time starts now, okay. You do not know how much time each simulation takes. So, you assume that each simulation will take about 1 hour, and then you took 24 points in this space, and then in some order you started going in this direction first, you went like this, okay. So, you covered these many points, 24 hours is over, you do not have information at these points. There is a problem with LHS, because the criteria phi was generated based on all these guys. Now, with this response you cannot make a wise decision, because they have actually taken these points into account, but you do not have the responses there. So, the space fillingness property is lost immediately. There is a problem with LHS. Instead, in such cases, what you can do is there is something called Sobol sequence. There are multiple other stuff. LHS is widely used, so we are talking about it. If you go to MATLAB, there is also an optimal Latin Hypercube sampling. This is a better way of doing this Max-Min algorithm. Okay. There is also a constrained Latin Hypercube sampling people do. Okay. Hammersley. There is something called a Hammersley sequence which you can use, and T stands for triangle, V stands for Voronoi, C is central, centroid, sorry, not central, centroid, Voronoi, tessellation, not triangulation, sorry. So, there are multiple other sampling schemes that you can use, but they also have these kind of space fillingness property, that is not a problem. Actually, this Hammersley and all has a very nice property, okay, more than space fillingness. What happens is they also have a memory, because when you do Latin Hypercube, even the optimal Latin Hypercube, sometimes you could get such big voids, okay. But Hammersley sequence has a memory property where it says is, oh, in that second iteration I put a point here. So, in the 8th iteration I will not have put a point right next to it while so much of space is unexplored. So, it will go and put this point elsewhere. Okay. So, that property is not there in LHS. It does not worry about your previous points. It is more like a, I do not want to use the word, but it is more like a stationary process. Okay. So, the interesting point of Sobol sequence is for any n and k being greater than 1, n is the dimension and k is the number of grids that we are talking about. The sequence for n minus 1, so you can take any n minus 1th dimension and k is a subset of the sequence for n and k. Understood what I am saying? You can reduce and it will still be a subset of it. Okay. What I am saying is these 4 did not run. Okay. So, you can take this, because this is in 2 dimensions that we are talking about. Okay. So, even any other projection that you take will be a subset of the original one. So, the uniformity in the sampling part, or in the sampling will be preserved. So, in that sense it is a good idea to use sequences like Sobol. Okay. I just wanted to pull a couple of example from our research study to show you where such things can be used. Basically, I am going to show you something on design of experiments right now, and the next example I will also show you a design of meta model. Of course, the meta model part we will discuss next. Okay. So, we are interested in designing a what means a vertical axis wind turbine. The type of wind turbine that we have designed is called Savonius. So, Savonius is a very simple idea. So, you can see that you can take a cylinder, okay. You can just cut it into 2 halves and it will become, you just move the center, okay. And this is how it looks like. Okay. Of course, it is mounted on a shaft, and as wind comes it starts rotating in a particular direction. Okay. So, what we wanted to do is this first benchmark, because we are interested in a computer model. So, this was done in a water tunnel in the applied mechanics department, and we created an equivalent computer model, and we wanted to evaluate this qualitatively. Okay. So, you can see the vortices formed in these regions are all captured well. That is what we wanted to do, okay. Because those will tell you what is the pressure, okay, and the vortices, those are the plots that you want to have. And there is something called the Strohal number. So, we are seeing that when the vortices are created, you can see the vortices is created and then it is leaving. So, the vortice will travel like this and then we will go and capture. So, within 1 second or over 4 seconds, how many vortices are being shed? Is that the same in the computer model? That is something that we wanted to check. Okay. But this was the initial benchmarking. Then we wanted to study which factors are important, stuff like that. So, the classical Savonius model has a blade like this, but then in literature people have suggested that a change in the design will help, okay, for obvious reasons, something like this. This is called a batch type model, this is what we have here. So, we wanted to parameterize, we wanted to see how much should be the arc angle, the blade arc angle, how much should be the blade arc radius, how much should be the rotation angle, how much, this is called the overlap ratio, how much should be the perpendicular distance, should it be close to each other or should it be far away. So, these are all parametric study, as you might know. So, first we wanted to parameterize them, and we also wanted to understand what is the effects on each one of them. These were from our experience as well as from the literature. So, we do a basic representation, parametric representation. Then what we have done is similar to the nested axis plot that I showed you. Okay, I did not show you a nested axis plot, I just showed you a tile plot, okay, but the same idea is here. But what is happening is currently we are investigating 4 variables in this, r, d, phi, theta and phi. So, the way this happens is I am going to fix theta at 7.5 for this particular tile, I am going to fix phi to be 117.5 for this particular tile. Within the tile r and d varies. Okay. So, in one shot I am able to visualize 4 variables. So, this is one way of doing it, but this is the maximum you can do. You cannot visualize 6 variables, for instance, you can only visualize 4 variables. Okay. So, today this visualization of data is a big stuff. Okay. Now, with all your sensors and all that, you get a lot of information, but what is the, how do you visualize this data in higher dimensions is a big problem. So, like this we see, and then we figured out that there are spots. This is coefficient of performance is something that we are plotting. Okay. We had to perturb a little bit, we have to run computer simulation, that is why we build the computer simulation to begin with. It is expensive, it is still a CFD model, it takes a few hours to run, but we did about, let us not worry. So, we did few simulations and then we have we have some zones of interest. Okay. This is just based on your nominal value and a little bit of perturbation, it is not the actual fitting. Then what we did is we took the n dimensional space, which is the 4 dimensional space, we put Latin Hypercube samplings. I think there were about 86 samples, 70 plus 16 samples at the corners we did, and then we fitted a surface to get the optimal result. Finally, the optimal results was also manufactured, and if you want you can see the stuff in the workshop, in our workshop it is there. Okay. This is another interesting problem that we work on as a crashworthiness design. So, in this is some picture that is lifted out of the internet. This is typically the car crash experiment, right. So, after this the car is lost, meaning you cannot use the car. So, you cannot use as many simulations as as many experiments as you want. So, computer simulations is a better way to do. This is a very interesting problem because material, geometric and large plastic deformations. Okay. So, material nonlinearity means large plastic deformation material, and there is also boundary condition nonlinearity is there, meaning you start with a boundary condition, but during the crash the boundary condition changes. So, it is a boundary condition nonlinearity is also there. So, this is an interesting problem because you want to minimize weight, at the same time you want to increase the energy absorption. Okay. You want to increase the energy absorption. And even in energy absorption, only in the frontal part you want to increase the energy absorption, okay, because if you want to do energy absorption, I can put a concrete. Of course, my weight will get affected, but I can put a concrete in the front, it will absorb all the energy, it will not send it to the dummy or the passenger. But there is a problem, because crash propagates this way and our inertia propagates this way. Okay. So, you will go and bang on the concrete. Okay. So, there is some head injury, neck injury criteria and all that people try to do. So, this is a conflicting objective right here. Okay. So, you wanted to minimize, but also you wanted to increase your energy absorption. So, you will have to come up with innovative materials and designs to do that, but that is not what we are focusing on. This is a simple crushing and buckling kind of an experiment that we try to do. So, the point is we took some 2 design variables, that T and L, and we have some displacement constraints. Okay. This says whether it failed or it is okay. Wherever you see the red circle, it is failed, and wherever you see the blue circles, it is the blue dots, they are fine. The point that I want you to look at is, this is out of an LHS design, do not worry about all that. Okay. L u, look at the function, it is very clear that beyond this it is failing, because that is what we have defined. If your displacement, the summation of the displacement absolute values, if it is greater than 0.05 or 0.06, it fails, that is what we are saying. So, that part is clear, but for small changes in L max. Okay. So, from here to here it was like this, for this value it goes up here, then it comes down, okay, or in between it went up here, it went here, it came down, then it is here, then it is going up, it is going up. Okay. If I connect it like that, it is a highly nonlinear function. Okay. I have so many realizations here, and for each realization I have points. I am not necessarily connecting it properly. Okay. Probably it is somewhere here, and then it goes up and then it comes down. So, it is a highly nonlinear function. Okay. Then there is a problem, do not worry about this. So, what we are trying to solve in that problem is, I will go back to that problem. What we are trying to solve is, we wanted to minimize the value, the volume, such that some energy ratio. What we are doing in this particular case is, for T and L, which are my design variables, there are different points, right. Through an LHS design, we are estimating what the energy ratios are, and we are fitting a surface. This is what we are going to talk about. This is a surrogate that I have fitted. Okay. Then this surrogate, let us call it G hat or whatever it is, it will be used here to do the optimization. This is something that we saw yesterday. If you have this function G hat, you know how to do the optimization, that is what we saw yesterday. But right now I only have a criteria, I did not have this equation, I do not have an equation of E over E t in terms of L and T. So, what I am doing, I am creating all these blue dots that are in space, which comes out of an LHS sampling, and then I run the simulations at each of this point, and then I am fitting a surface. We will see how I fit the surface in the next module. Okay. Once I do that, I will be able to use it here. Okay. But it does not stop here. We will also say in the problem that the probability of failure should be less than some target probability of failure. Okay. That is slightly out of scope, but I will also tell you, So, what happens is, when this function was so nonlinear, what we try to do is we try to take a slightly different look at it. Okay. We took it in terms of the design space, okay, not in the output space, but only in the design space, and this is what we call the island failure zone, meaning because this is also good space, this is also good space, this is the failure zone. Okay. We use some computational geometry technique called convex hull to do that, but unfortunately it also includes some good points, but we were able to do some work with it. Okay. But later we came up with some technique called the alpha shape, which will do something like this. Okay. That is not the point of the discussion. So, what we do in this is, after all this, you will not take this point to be, this point is outside, you do not take that to be an optima, because what we are saying is, there is some randomness in T and L. For a small randomness, this will actually fail. Okay. So, how usually we take that into account in our deterministic design is, we use a 1.5 safety factor, so that this point gets pushed here, which means it is a heavier design, okay, but still it is safe from these perturbations, small perturbation or small randomness. This could be a manufacturing error. You ask him to generate like 5 mm, but he did 4.8 mm. You put it in the car, your car will immediately fail. Okay. So, you want to push it that side. So, let us say that this was 6 mm. So, even if he gives you 5.8, you are okay. Okay. So, it means that it is a over design, but we wanted to minimize this over design. Then what people say is okay, we know that this follows some kind of a distribution, and then they estimate what is the failure. They do not work for 0 failures, they try to minimize the failures as much as possible, that is the paradigm. Okay. So, we have used, so what I am trying to tell you is, this kind of gives me an idea on the design space. I do not have to do an optimization with this per se. Okay. Right now, that is what some of students are trying to look at is, how does the design space vary? Does it even, because you will see in the next surrogate model, you need to know, at least you need to have some idea of your function, then only you can fit a function to it. You cannot say that I have zero idea about how the function varies, then meaning like that is not a wise way of approaching the problem. Okay. So, you need to have some understanding of how the function is going to vary over your design space, so that you can do that. Okay. Then finally, I mean in this particular stuff we also did a what you call an optimization study, and then as you can see that we had some failure probability, but interestingly in this point there is a local optima was there. Okay. So, this was the, let me see, yeah, this is that failure probability constraint that we have. This is our W times T, I guess, the objective function. These are the objective function. This is the failure curve for the reliability, okay, and this is that I should have used a different curve. So, this is the energy curve that we are talking about. So, if you did a starting point from here, it will reach here. If you did a starting point from here, it will reach here. So, this was a classical case of a multiple local optima case. Okay. So, we first did, and accidentally while running the algorithm again I gave a different, I mean I did not intentionally give a different starting point, I did, and then we went and plotted and saw, then we understood that it was like this. So, it is always suggestible when you use a gradient based algorithm, which was mode of its use, is to use different starting points. Okay. Fine. This results were just shown to you to motivate where all you can use design of experiments. Okay. You can, for understanding the design space, to understand this, to do to factor analysis we can do. Okay. And of course, you can also use it for optimization obviously.